Welcome back. In a previous segment, we discussed the exponential functions, whose rate of growth is excessively large. In this third segment, we're going to study another class of functions called polynomial functions. So let's define them right away. A polynomial function, f of x, is a function that can be written like this, as the sum of n plus 1 terms, where each term is a product of a real number and a power of x. So notice we have in this formulation n plus 1 terms called a sub 0 up to a sub n. These are called the coefficients of the polynomial. Now, of course, some of these coefficients may be 0. So, for example, if a sub 2 is 0, then this term disappears, and this polynomial function would not contain an x squared term. Also note in particular that a sub 0 is a constant real number, which is the same as a sub 0 times x power 0. So the subscript of the coefficient is always equal to the power of x that it multiplies in the polynomial. Now let's assume that a sub n is different from 0. In other words, n is the subscript of the coefficient in front of the largest power of x in the polynomial. Then n is called the degree of the polynomial. So as an example, let's go back to a function we studied in previous videos. F of x equals 999 times x squared. Well, this is a polynomial function because it's the sum of terms, each of which is the product of a real number, in this case 999.0, and a power of x, in this case x squared. So in this particular case, the largest power of x is x squared, so the degree of the polynomial is 2, which means 999 is the value of a sub 2. Now notice there are no other terms in the polynomial, so we know that a sub 1 is 0 and a sub 0 is also 0. So that was a very simple example of a polynomial function. Now let's go back to the general class of polynomial functions and state a general result about them in terms of big O relationships. So theorem 1 in this lecture says that any polynomial function of degree n is big O of x to the power n. Remember, what this means is that take any polynomial function whose degree is n, it says it's upper bounded asymptotically by the function x to the power n. So we're going to prove this using a direct proof. Notice that the statement of this theorem is really a universally quantified conditional. It says for any polynomial function, if the degree of that function is n, then the function is big O of x to the power n. So let's take an arbitrary function f of x of degree n. Now remember that at the end of the proof we're going to use universal generalization to generalize whatever result we prove to all polynomial functions, and therefore proving the theorem. But from now on and until then, f of x is an unknown but specific and arbitrary function, polynomial function, which means a sub n minus 1, down to a sub 0 are all specific but unknown and arbitrary real numbers, making up the definition of the polynomial function that we chose arbitrarily. Now, direct proof means you assume the truth of the hypothesis of the conditional and you prove its conclusion. So what's the hypothesis here? The hypothesis is that f of x has degree n. So what that means in particular, and write it down in your notes, is that a sub n must be different from 0. On the other hand, all of the other coefficients may or may not be equal to 0. So we assume that the polynomial has degree n, and now we need to find an upper bound for the absolute value of f of x in terms of this function. So the first step in the proof, having made those assumptions, is to take the absolute value of both sides of this equality. that clearly follows from this line. Now to proceed, let me remind you of a well-known inequality. Let B, C, and D denote any arbitrary real numbers, positive or negative. If you take the absolute value of that sum, it must be less than or equal to the sum of the absolute values of the individual real numbers. Now remember, B, C, and D might be negative, but when you take their absolute values and you add them up, you're adding 3 positive numbers, and that sum must be larger than the absolute value of the original sum. Make sure you review that result and you convince yourself that it works and it's always true. Now we can use it to upper bound this expression. Notice this expression is the sum of this real number for particular x, this real number, and so on and so forth. So when we take the absolute value of the sum of these numbers, it must be less than or equal to the absolute value of this term plus the absolute value of that term, etc., etc. We're extending the previous result from 3 real numbers to, in this case, n plus 1 real numbers. So here is what we can infer right away from this equality. We can infer this inequality. Again, I took the absolute value of all the terms in the polynomial function. So what we have now is we prove that the absolute value of f of x is less than or equal to a sum of terms. Now let's focus on each one of these terms. Well, each one of these is the absolute value of the product of 2 real numbers. So let's see what we can do with that, and let me remind you of a well-known inequality that says the absolute value of the product of 2 numbers is less than or equal to the product of the absolute values of these numbers. Again, this is just a matter of checking the sign of these numbers b and c. So this inequality holds for any 2 real numbers b and c, therefore they're going to hold for any values of the coefficients and the specific values of the powers of n. So in conclusion, what we can infer from that is that each one of these terms is less than or equal to the product of 2 absolute values. Let's write this down. Now notice for the big O relationship to be proved, we need to upper bound f of x by x to the power n times a constant. So we're going to try to get rid of, we got x to the power n here, but we're going to try to get rid of these lower powers of x. And so to do so, we're going to factor out this largest power of x, x to the power n. And therefore we're going to get the following expression. Now the problem here is to do so we need to divide some of the terms by a power of x. So this expression only makes sense if the denominators here are different from 0. Well, an easy way to enforce that is to assume that x is different from 0 and then all of the powers of x are different from 0. But actually in big O relationships we only care about the end behavior of f when x is large enough. So instead of saying x is different from 0, let's just assume from now on that x is strictly greater than 0. Therefore, if x is large enough, then this number is different from 0, so is this one and that one and so on. Therefore, this expression here is equal to that one. And the advantage of that is that now we have isolated the x to the power n function that we need in this big O relationship. So what we have shown so far is that the absolute value of f of x is less than or equal to a power of x times this big expression here. Unfortunately, this expression is not a constant. Notice it's the sum of fractions, and each fraction has a constant as the numerator and a power of x as the denominator. So in other words, this expression here is not a constant because it depends on the value of x. However, it's pretty easy to upper bound this expression by a constant simply by realizing that the value of this fraction, for example, will be less than this constant here if and only if this power of x is greater than 1, because dividing any number by a number that's greater than 1 gives a smaller number. So all we need to do is to assume, for example, that x is strictly greater than 1. In this case, every power of x all the way down to x power 1 will be greater than 1, and therefore every fraction here in this expression will be strictly less than or equal to the numerator. So let's write this down. We have this inequality now, which holds only when x is greater than 1, as we just argued. So we see that the absolute value of f of x is less than or equal to a constant times the absolute value of x to the power n if x is large enough. In particular, we proved then that f of x is big O of x to the power n with particular values of c and k, or witnesses, equal to what? Well, k is simply equal to 1, and c is equal to the sum of the absolute values of all the coefficients in the polynomial function. So, remember that this result only holds for an arbitrary but specific function f. So all we need to do now is to apply universal generalization. Since f is arbitrary, we just prove the theorem, which is any polynomial function of degree n is big O of x to the power n. And this concludes our proof.